As I mentioned at the start, I'm John T. I'm Professor of Astrophysics here. And a lot of the work I do is exoplanets and is searching for life elsewhere. But what I'm going to tell you about tonight are the objects that were a big part of me developing my passion for astronomy in the first place, and something that I've continued to research for my life, and something that, with the amateur astronomer in me, the person who will go and sit out under the night sky. So just like Uncle Wayne was talking about lying out under the stars, I still have that passion for looking at the night sky. And comets are one of the things that I am most excited, most fascinated by, most passionate about. And it was fabulous. I was so honored for Uncle Wayne to come and give the introduction. And it astonishes me as somebody who grew up in the UK to actually be here on a continent with a history and a heritage for astronomy stretching back 65, 70,000 years or more, with knowledge that has been passed down. Now, comets have been part of that. They are something that we look up at the night sky and we look with wonder. And what we tend to do is we tend to get very familiar with the sky above us as it goes year by year, the constellations. We know that, for example, in our winter here, we get the Milky Way high overhead. We get Scorpius and Sagittarius bright in the sky. In our summer, we have Orion very, very visible. And we're familiar with the constellations shifting from month to month, year to year. But comets are transient temporary visitors. They appear, they can be very spectacular, then they go away again. And people have had a really long heritage all across the Earth of looking up at the night sky and associating the things they see there with events that are happening on the Earth. And so when you see something unusual and bright and spectacular in the sky, people quite often have historically associated that as being a portent, as being an omen, as telling you something strange is going to go on in the future or has just done in the past. And of course, my zapper's decided to go to sleep, so I'm just going to wander over here and make the computer go bingle, bangle, bongle at me a second. And then it'll, there we go. It's a happy music of waking up again. So hopefully that will now work. If it doesn't, I know what the problem is. And I can go like that, and that should do it. There we go. So I've got a couple of examples of this from history. And there are examples from European history where we've actually got quotes that have been passed down. The first of them, and this is not the photograph of the comet in question, is going back more than 2,000 years ago. This is at the time of ancient Rome, and one of the great enemies of ancient Rome was a guy called Mithridates, or Eupator Dionysius, who was born in 135 BC, died in 63 BC. And there are quotes that have survived to this very day about this person who was fairly legendary. It was said that when Mithridates' sixth Eupator was born, a comet burned so brightly for 70 days that the entire sky seemed to be on fire. In its greatness, it filled a quarter of the heavens, and with its brilliance, it outshone the sun, whilst its rising and setting took a period of 4 hours. So people are looking up at something spectacular in the sky and tying it to the events on Earth, the birth of this great man who did great things. Another quote, heavenly phenomena had also predicted the greatness of this man. For both in the year in which he was born and the year in which he began to reign, a comet shone through both periods for 70 days in such a way that the whole sky seemed to be ablaze. Tells you the degree to which comets at their brightest, the great comets that we see, capture people's imagination and the importance that people in ancient cultures placed on them. Another famous event that happened in the Roman Empire was the death by stabby. Very democratic process. It was one man, one stab. This was the end of Julius Caesar in 44 BC. And at this time, shortly after Caesar was stabbed to death, we had an incredibly spectacular great comet, intrinsically one of the brightest comets seen in the last 2,000 years. Recorded by the people at the time, among the divine portents, there was also the great comet. It appeared very bright for 7 nights after the death of Caesar, then disappeared. And at the time, they considered it to potentially be the soul of the great emperor rising to the heavens. That was probably one of the most spectacular comets we've seen for 2,000 years. It was visible in the daylight for about a week. It was probably visible with the naked eye in evenings for more than a month. Really incredible object. From my own background, growing up in the UK, one of our earliest scientific records is an incredibly woven beautiful tapestry called the Bayeux Tapestry. It's a record of the events that happened in 1066 around the Battle of Hastings. William the Conqueror invading, King Harold fighting back. The record woven by the victors, of course, and this was shortly before King Harold got shot in the eye with an arrow, the famous scene. So he was having a bad day, and you see all of Harold's minions here pointing up at the sky at this spectacularly woven apparition in the sky. That was Comet Halley, which is probably the most famous of all comets. Last visible in 1986, coming back in 2061 when it will be markedly better than it was in 1986. For the younger people in the audience who are optimistic about a long and healthy life, make it to 2135 and Comet Halley will be astonishingly spectacular. That will be Halley's best apparition since about 838 AD, and that will be awesome. So a good reason to get rejuvenation treatments and try and look forward to your old age, I guess. But again, this is a woven tapestry recording a great battle, recording an epochal event in British history. And the comet that was visible in the sky was considered important enough to include when they were making this record. It's not just in European history. All around the world, people have seen fabulous comets. This is a comet called Ikeya-Zhang from the early 2000s that was last seen in the 1500s, goes around the sun every 400 years or so. These are records from different cultures of comets long past. You have images here from a silk record from China, again from more than 2,000 years ago. I think this is from about 200 BCE. Records of different comets that have been seen. Note this one here that looks strangely like a symbol that you don't often see very much anymore. There are discussions that I've read in research literature talking about the commonality of that swastika symbol, this swirly symbol with bent arms, typically 4 of them, which has occurred all around the world in many different cultures before those cultures were in contact with one another. And one of the suggestions is that it could actually be something that is born of a particular comet in the past that was very active in 4 locations and gave you an object looking just like this. So there may be links between the symbology of humans and the things we've seen in the sky. But these are records of different broom stars that were seen from China. This is a Babylonian tablet recording observations of Comet Halley in 164 BCE. Now, these ancient observations are incredibly useful to us as astronomers because they allow us to track back the history of these objects and learn more about them, to piece together a narrative on a timescale longer than that we normally talk about. When we normally talk about astronomical observations, as Graziella did, we go back to Galileo, to the birth of modern astronomy with the telescope. But comets moving around the sun go around quite often on timescales much longer than that. The rarest astronomical events happen on timescales much less frequent than that. So having these ancient records, having narratives passed down through oral history here in Australia, is an incredibly powerful tool for us to expand our knowledge of astronomy on a longer timescale than we can do just using modern records from the last 400 years. The record here is really interesting. This is from the notebook of a great observer called Tycho Brahe, who was probably the last of the great observers before the dawn of the telescopic era. This is a great comet of 1577, portrayed here in a beautiful artwork showing people below in their fancy dress looking up at the comet that spanned the sky. Now, this in many ways was really the dawn of modern science when it came to comets. Brahe was a very peculiar individual. He was a wealthy guy, Danish, who in theory is recorded as having died of politeness. He was part of the nobility and he couldn't offend the king, and he needed to go to the bathroom but couldn't ask to go to the bathroom, and eventually died of a ruptured internal organ as a result of it, allegedly. He had a pet moose that got drunk and fell down the stairs. He had a pet dwarf, and he also had a silver nose because he lost his part of his nose in a duel. Real peculiar individual. He was also, though, an incredible observer, probably the best of his generation in this time before we had telescopes. And when this incredible comet came through the solar system, he was tracking its position. Now, the quirky thing that you'll see in this figure is the Earth is at the center of the universe in his plot here, with the sun moving around. And one thing that he noticed was that the tail of the comet was always pointing away from the sun. That was one of the things he wrote down in his notes. But the other thing he did was he tried to measure the distance to the comet using a technique called parallax. Now, we use this to measure the distance to stars, but you can do it for things that are closer as well. If you hold your finger up in front of your eyes and you look through one eye and then the other and back again, you'll see your finger appearing to jump back and forward. And the further your finger is away, the smaller that motion is. Now, when we use this to measure the distance to stars, we measure from one side of the Earth's orbit, and then 6 months later we measure again. So we make our eyes 300 million kilometers apart. But you can also use what is called the terrestrial parallax, the diurnal parallax. The Earth is turning. So if you observe an object, when that object's rising, and then observe it when it's setting, your observation positions are probably about 12,000 kilometers apart because you're on opposite sides of the Earth. A bit less if you're up near the poles where Brahe was. He realized he could use this technique, and people had used this technique to try to measure the distance to the moon. And he wanted to measure the distance to comets because the prevailing theory at the time was that comets were atmospheric phenomena. They were much closer than the moon. They were in our upper atmosphere. He measured the distance to the comet and he couldn't get a satisfactory answer. His parallax was so small. But what he found was that it was at least 3 times further from the Earth than the moon was. Now, in reality, it was much further away than that. We now know that. But this was the first real indication that comets were significantly further away than our satellite, and they were definitely not atmospheric phenomena. We move forward to 1682 to Sir Edmund Halley, the second Astronomer Royal in the UK, a guy who was great friends with Sir Isaac Newton. And shortly before this, Sir Isaac Newton had published his masterpiece, the Principia Mathematica, which laid down the fundamental rules of Newton's gravitation, giving us mathematical tools that allowed us to work out how things moved through the solar system. Now, by this point, we'd realized that the Earth was not the center of the universe. The sun instead was at the center of the solar system and the Earth was going round. But the prevailing view of comets at this time was that they moved through, came past the sun and then disappeared, never to return. Halley saw the great comet of 1682, spectacular comet in his sky, and he went back through the written records of comets that had been observed in the last 300 years or so. And he found that the comet of 1607 and the comet of 1531 had moved in a very similar fashion across the sky and through the solar system as the comet that he'd seen in 1682. So he made the great conceptual leap. He said, this comet is bound to the sun and it's moving around on an elliptical orbit. It's not leaving never to return, but it will come back again. And he forecast that this comet would return in 1758. Now, in the intervening years, people got really interested in this. Do comets really come back? Can you predict the return of a spectacular comet? So when 1758 came around, astronomers scoured the sky month after month to no avail. On December 25th, Christmas Day, genuinely, Halley's comet was recovered by Johann Georg Pallich, who was an amateur astronomer and a farmer, I believe, in Germany, who spotted it low in the sky, picked it up, and that was a confirmation. Comets come back. They orbit around the sun periodically, rather than being one-time visitors tearing through, never to return. This artwork, incidentally, is showing Comet Halley as it came through in 1910. Came past the Earth relatively closely. It was very bright in 1910. Missed us by a whopping 15 million kilometers, but that's a near miss in astronomical terms. But it lined up just perfectly that Comet Halley's tail swept across the Earth. This led a famous astronomer at the time, Flammarion, to suggest that the cyanogen that had been detected in cometary tails could pose a very real risk to life on Earth, as that gas suffused the atmosphere. Led to a huge number of cranks making a fortune from selling anti-comet pills. Keep yourself safe as the Earth passes through the tail of the comet. Now, clearly the prediction didn't come true because we're here to talk about it, but it shows the way that the science has developed, I guess. The next step in the story of our understanding of comets towards a modern understanding came with a comet called Comet Lexell. The story here is in the year 1770. There was a great astronomer called Charles Messier, who is beloved of the amateur astronomy population because he created a catalogue of fuzzy blobs called the Messier catalogue. These are like barcode numbers for cool things in the sky. There's 110 of them, although he probably only catalogued about 100 and 300 and 4, and a few more were added in the aftermath. One of them actually is a gap in the catalogue because nobody can work out what it was that he catalogued. The Orion Nebula, Messier 42, the Pleiades, Messier 45. These are kind of the go-tos when you're learning to use a telescope of really good things to look at. And if the skies are clear on Saturday night after the Curious Kids panel, the wonderful Roger and Robin may be able to show you some of these through the telescopes. We'll do a bit of stargazing. Messier created this catalogue, not because he loved those fuzzy blobs, but because he found them inordinately annoying. Because he was a comet observer. He loved looking for comets in the night sky, and so he scoured the sky with his telescope, looking for fuzzy blobs that moved. And he kept finding these fuzzy blobs in the same places that he got all excited. He thought he found a comet, and then was disappointed because it's the Orion Nebula again, right? So he made this catalogue. But on 1st of June, 1770, he discovered a comet. And at the time it was fairly dim, but it quickly brightened, and within a month was as bright as the brightest stars in the sky. But it was unusual looking. It was a big fuzzy blob. It didn't really have a spectacular tail. And it also moved across the sky at a remarkable rate. At its fastest, 40 degrees an hour. Really fast, really unusual. By this point, people had worked out how to figure out the distance to comets and also from the measurements how they moved. And what people quite quickly realized was that this comet had come close to the Earth. It is still the closest confirmed cometary approach to the Earth on record, missing by a couple of million kilometers. It's known as Lexell's comet, not Messier's comet. Normally comets are named after the people who discovered them, but there are a small number that are named after the mathematicians that worked out their orbits. Comet Halley, been observed for thousands of years, named after Halley because he worked out the orbit. In this case, Comet Lexell was named for Lexell, who was a mathematician that worked out the orbit. When they looked at how this thing that nearly hit the Earth was moving, they found it was going around the sun with a period of just less than 6 years. Now, this is shocking. Here's a comet as bright as the brightest stars that goes around every 6 years. So the obvious question is, if it was seen in 1770, why didn't we see it in 1764? So they ran it back and they found that in 1764, it would have been on the far side of the sun, and so it would have been hard to spot. So you'll give people that. Why didn't we see it in 1758? Well, it turns out that in about 1760, 1761, when this comet was furthest from the sun, it was actually at that point following an orbit that brought it nowhere at all near the Earth. But it came very close to Jupiter. Jupiter's gravity grabbed the comet, flung it onto a new orbit. Now, this is me using paint, so please excuse the quality of the artwork. Took it from this orbit that came nowhere near the Earth, grabbed it and threw it at our planet. You got the near miss in 1770, when it nearly hit us. Why haven't we seen it since? What about 1776, 1782? Well, it turns out that this comet was going around the sun with a period almost exactly half the orbital period of Jupiter. So it swung in, missed the Earth, swung back out. And by this point, Jupiter was all the way over here, so nothing happened. Swung through again, was on the far side of the sun from us, we didn't spot it. And when it swung out again, Jupiter was there waiting for it. And Jupiter's gravity got hold of it and threw it away. Our observations are not good enough to know exactly what happened. Jupiter could have flung it hard enough to never return to the solar system, or it may have joined a population called the Centaurs and be still out there, floating in the icy depths of the outer solar system. We just don't know. But what this showed us was that not only are comets moving around the sun on elliptical orbits, coming back time and time again, that they are the victims of planetary pinball, that they get bounced around the solar system from pillar to post, get flung onto new orbits. They're changeable, ephemeral objects. Now, I'm talking a fair bit about great comets. In any given year, there are 20 or 30 comets that are visible if you've got a good telescope. But only a handful of them will get bright enough to see with the naked eye. On average, about one comet per year is visible from the naked eye as a very faint, fuzzy thing from a really dark site. But occasionally you get a comet that is so bright that it's visible to such a level that members of the general public who are not really looking for it will see it and go, wow. That it's bright enough to see from big cities, as bright as the brightest stars. In the 45 years of my life, we've had 4 great comets. And these are those great comets. The top 2, that is actually my own photo from when I was a teenager, which is why that's in. There are much better photos of that comet available, but I did that. That was cool. At the top left, we've got a comet called Comet Hyakutake. Came past the Earth in 1996, was very well visible from the northern hemisphere, not from the southern hemisphere. So it passed above the Earth's north pole. Came relatively close by, nowhere near as close as Comet Lexell. So it was a fairly active, reasonable sized comet that came close to Earth and got very bright. At its best, it was as bright as the brightest stars, and it had a tail stretching 100 degrees across the sky. Really incredible. Visible with the naked eye for a few weeks. Comet Hale-Bopp, which is this thing here, was something else entirely. It smashed the records for the longest time people have been able to see a given comet with the naked eye. Was visible with the naked eye for 18 months continuously. Widely seen from both hemispheres. This is me observing it with my parents, who are at the back of the room here, from a place called Kielder in the north of England. And I dragged them up there as a teenager because we had to get photos of this comet on slide film, and spent a fortune taking 30 photos and sending them off to be processed, and we had to wait a week to get them back and then look at them and see that most of them were rubbish. But we were out observing this comet, and this is pretty big on the sky. The length of those sails are equivalent to your fingers outstretched at arm's length, so pretty spectacular, really visible. And suddenly there's this bit of light peeking over the horizon. We're thinking, is there a car coming? Is there something like that going on? And no, it was the northern lights, so we got the comet and the aurora on the same night. So I always like to include that. That was, for me, the greatest comet I've personally seen. At the lower left, and a comet that will feature on a lot of our slides tonight, is Comet McNaught, which was the great comet of 2007. Now, this was spectacular from the southern hemisphere, reasonably good from the northern hemisphere. I saw it, but it wasn't all that from the northern hemisphere. At its brightest, it was visible in broad daylight, with just a few degrees from the sun. There were reports of people who put their hand up and blocked the sun, and you could see it there. That's how bright it got. For scale on this picture, that's the full moon. So that was astonishingly spectacular. This one here is Comet Neowise, which was visible in 2020. Again, it wasn't that impressive from down here. It was at its best from the northern hemisphere, where it was really spectacular. Not a match for McNaught, but 45 years, 4 comets that were great comets. And on average, if you look back over previous decades, roughly 1 every 10 years. But they're like buses. As we saw in 1996, you wait 20 years and then 2 come along at once. These were both in the sky at the same time, which was just bonkers. But how do they work? I'm showing you all these wonderful photos, and again, the glowy blob at the bottom is a full moon for scale. Comet McNaught was ridiculous. How does this work? What do we have? What's the anatomy of a comet? Well, at the heart of these spectacular objects lies a snowy dirt ball, a dirty snowball, an object that is debris left behind from the birth of the solar system, that is a mix of rock and dust and icy material, volatile material. Mainly water ice. Water in solid form is one of the most common things in the universe. Always makes my head hurt a bit when we say that water's rare. It really isn't. 74% of all atoms in the universe are hydrogen atoms. It's the most common of all the atoms. Oxygen is the 3rd most common atom, 1% of all atoms. Put hydrogen and oxygen together and you get water. Water's everywhere. And so once you're beyond the snow line, as Graziella mentioned, suddenly everything's made of ice. These things form far out. So you've got these dirty snowballs. These are ones we've visited with spacecraft, Comet Halley, Comet Vil-2, Churyumov-Gerasimenko. Dirty snowballs. When they're far from the sun, they're cold, and that's all you'd see. Little floating lumps of ice, nothing going on. But as they get closer and closer to the sun, their surfaces heat up. And the volatile material on the surface starts to get excited. You see here Comet Churyumov-Gerasimenko as it's saw from Rosetta, the spacecraft, and you see all these shrieks and jets coming off it. If all of the surface was bare, exposed ice, ice would be subliming at all locations. Sublimation is what you get when you have an ice that is too hot to be an ice, but there is no pressure to allow it to be a liquid. So the ice becomes a gas without becoming a liquid in the middle. We say it sublimes. And as this volatile material heats up, it eventually reaches a point where it sublimes. But through most of the surface of the comet, the rubble and the dust and the debris insulates and blocks it. So you get active areas where there is some exposed material. Or it might be that the heat penetrates deep enough and vaporizes a pocket a bit deeper down. And that material jets off into space, carrying with it dust and debris. So a comet begins to shed material to space. And an average comet, on an average pass by the sun, will lose about 1 meter depth of its surface on average per encounter. So they're gradually wasting away to space. All that gas and dust shed into space shrouds that dirty snowball in what we call a coma, a cloud of gas and dust all around it, diaphanous and shimmering, beautiful. And this is when the comet starts to get brighter for us to see. In the middle there, you've got a tiny little speck that doesn't reflect much light and is very dim. You surround it in gas and dust zone, that's a big reflective area, bouncing sunlight back to us, and that's what we see. So you get the coma, gas and dust surrounding the snowball. That gas and dust is then pushed away from the sun by radiation pressure and the solar wind. And it follows different paths. This is Comet Hale-Bopp again, and the blue here is what we call the ion tail or the gas tail. The molecules of gas are exposed to the ultraviolet of the sun's radiation and become ionized. The electrons are stripped away. And at that point, they feel the sun's magnetic field and they feel the solar wind, which is charged particles flowing out from the sun at high velocity. And that picks up that gas and pushes it directly away from the sun at very high speed. So the ion tail, the blue gas tail, points directly away from the sun. And we can use it to track what's happening with the gustiness and turbulence in the solar wind, because you will see structure in it, you'll see breaks in it as a gust of wind blows past. Behaves very much like a windsock. The yellowy, whitey, creamy colour tail is a dust tail. That's all the dust particles that are lifted off the surface of the comet. And they feel the wind and the radiation pressure as well, but because they're larger and more massive, it is less effective on them. So they move away more slowly from the comet. So they're still pushed away, but you get this curved, sickle-like, scimitar-like tail, which reflects a little bit of the comet's motion, as well as the pushing away from the sun. So this tells you that one of the things that every, cheap Disney movie tells you about comets is wrong. The comet tail will always point away from the sun. So that means when the comet's coming in, the head is in front and the tail's behind. But when it's going back out again, the tail is in front and the head's behind. So the head is towards the sun, the tail is away from the sun. So we know from that the sun was down here. There are reports and photographs through history of comets with multiple tails. You have here Aaron Rowland, a comet in 1957, with a sunward spike and anti-tail. The anti-tail is a quirk of geometry. When the alignment's just right, the dust tail is actually pointing away from us to such a degree you're kind of seeing part of it there. It's all a line of sight effect, but you can get a part of a comet's tail at least pointing towards the sun. Here you've got Comet de Chezeaux in the 1700s. Several clear striated tail fragments, 6 or 7 tails there. Comet West in 1976, the same kind of thing. We've got here a fairly faint comet from 2022, Comet ZTF, with a little bit of a sunward spike again, but I've included this even though it was a dull comet, because you can actually see the fan of the dust tail here, and you can get a feel for that line of sight effect that is creating that illusion of a tail pointing towards the sun. It's actually pointing away from the sun, but the comet's kind of between us and the sun, so away from the sun is towards us. That's kind of what's going on. And of course, here again, we've got Neowise from 2020, and you see a hint of what's going on with the multiple tails. So what's the story? Aside from the fact that the zoom bar is blocking my caption, but never mind. This is Comet McNaught, and this is one of the most astonishing photographs I've seen. This is Comet McNaught imaged in the morning sky and in the evening sky at the same time. The comet was a morning object after it was an evening object, and I might be getting those two the wrong way around. It could have been evening, then morning. So here is where it was, here is where it is. It's moving along this path around the sun, which is in the middle here, shedding dust as it does so, and that dust is being gradually pushed away by solar radiation. What you're seeing with these strands of dust out here is that they are material that was shed by the comet when it was here, and they're being pushed out from there in that direction. These ones here were shed when it was here. The further away they are, the smaller the dust particles, because they feel the wind more strongly. The bigger the dust particles, the less far they go. So that's what these dashed lines here are trying to show you. Big grains will be here, smaller grains, and so on. So any given spike is all dust that was emitted at about the same time. The smaller dust is further away, the bigger dust is closer in. The spikes themselves are because on this comet, there was one particularly active area, and the comet's spinning, just like the Earth. When the active area points towards the sun, it turns on, jets material into space, turns off a bit at night, turns on again. 1 day, 2 days, 3 days, 4 days, 5 days. Days is measured on the comet with its spinning and its tumbling. And the curvature is the path it's following around the sun. So that's why we're getting the multiple tails. It's a combination of the fact that this comet came very close to the sun, it whipped around very quickly, and it was spinning and tumbling as it did, so the activity was turning off and on, off and on. I guess it's a bit like a whistling kettle, where when the kettle's just starting to whistle, the little lid pops up, shuts down, pops up, shuts down, so you get bursts of steam coming out. Same kind of idea. That's what's going on, and that's why you get the multiple tails. That's how comets work. We have, as scientists, this overwhelming urge to categorize and to break things down into different groups, which is why we always end up talking about Pluto and dwarf planets. But for comets, we've historically broken them down into two categories, the long period comets and the short period comets. Now, this has a long historical background, which is that when people first thought up this classification, we had about 200 years worth of comet records. So any comet that came around the sun with a period of less than 200 years, we'd have a chance of seeing more than once. Anything with more than 200 years, we'd have only seen once. So more than 200 years is long period, less than 200 years is short period. A better shorthand is to think that the comets that are short period have orbital periods compared to human lifetimes. Comets that are long period are an entirely different beast. So this is I love showing this still. It dates back to the late 1990s from Newsweek when people were talking about Comet Hale-Bopp and Hyakutake. And they were comparing them to other comets from the last couple of decades. Now, the immediate way you can tell this is from the late 1990s is that Pluto is on it as a planet. So that dates this. That tells you how old this is. But it shows you some of the great comets of the second half of the 20th century, with Comet Halley in the 76-year thing for scale. Comet Kohoutek in 1973 is a salutary tale for later on in this story. Oops. So we have these comets that were seen through the second half of the 20th century. Kohoutek is an important one for me to discuss. When it was discovered, it was the most distant cometary nuclei detected on its way into the inner solar system. It was found further from the sun than any comet before. And that was really exciting because that indicated that it could get really bright. It was also destined to get very close to the sun, and that's usually a really good sign. So it means the comet is destined to be really bright. The closer it is to the sun, the hotter it gets, the more active it gets. But also, the closer it is to the sun, the more intense the solar radiation on it to reflect from it. So you have a couple of factors there that come together. So the media went hyperbolic. Comet of the century discovered. You're going to be really excited. Comet Kohoutek turned out to be a really good comet. It was a naked eye comet. It wasn't quite good enough to be a great comet, but not far off it. But because people have built it up so much, it has gone down in the annals of history as a spectacular disappointment. Those were the newspaper headlines. People were really underwhelmed by it because they expected something better. If it had not been bulked up so much, it would have actually been a really popular comet. What had gone on, as we realized, was that Comet Kohoutek was coming through the inner solar system for the very first time. So it had a lot of icy material on it that would evaporate at great distance from the sun, that would sublime, making it active further from the sun than normal. It had this burst of activity due to things like carbon monoxide, things like that, which is common in comets coming through for the first time. That made it brighter than it ought otherwise to have been far from the sun, made us overestimate how bright it would get. Still turned out to be pretty good. It will maybe do better when it next returns into the inner solar system, which is, I think, in about 2 million years' time. So long period comet really has a meaning. Comet West, which came through in 1976, was a great comet. It was a bit overlooked by people, partially because Kohoutek was such a disappointment to them. It's a boy who cried wolf thing. You told us that Kohoutek was going to be awesome and it wasn't. Why should we bother? But the other problem with Comet West was that it was a morning object. It was most spectacular in the hours before dawn. And it's a lot easier to stay up till 10 p.m. to see something than to get up at 3 a.m. to see it. But Comet West was really spectacular. It fell apart into 4 pieces, released loads of dust, got really bright. We'll probably be back in about 250,000 years. Hyakutake, I've already mentioned, 1996, whizzed fairly close to the Earth, pretty active, really spectacular, back in 25,000 years. And then we have Hale-Bopp. Hale-Bopp was astonishing. It was the biggest cometary nucleus we've seen for about 300 years, visible with the naked eye for 18 months. It was last visible when the Egyptians were building pyramids and will return in the year 4400, give or take. So they're your long period comets. They go around the sun with such long periods that it's many lifetimes before they return. The other population of comets, and astronomers being wonderfully inventive, are the short period comets. These are the comets with orbital periods measured in years or a few decades. You have here Comet Holmes, which was spectacular in 2007 because it had a comet quake, burped out a load of dust and got 1,000,000 times brighter than it should have been, becoming easily visible to the naked eye. The short period comets are things that you can see multiple times in a lifetime. Most of them are fairly dim and faint. You need a telescope to see them. Comet Halley and Comet Swift-Tuttle are the two brightest of them, with periods of 76 and 130 years respectively. But the great majority of them move on orbits around the sun with their aphelion, with the furthest point from the sun near Jupiter's orbit. You've got the orbits of Mercury, Venus, Earth, Mars, Jupiter, and Saturn here. And each pink circle here is the orbit of a short period comet. We know a few hundred of them. This tendency for them to have their aphelion near Jupiter is exactly what we saw with Comet Lexell. They've been grabbed by Jupiter's gravity and flung to the inner solar system. Jupiter slinging snowballs our way like a participant in a snowball fight, slinging objects our way. Now, we also now have found interstellar comets. Well, one of them at least. This is Comet Borisov from a few years ago. This is a comet that was passing through the solar system at such a speed that it clearly didn't originate here. If you took it infinitely far away from the solar system, it would still be traveling at 6 kilometers per second. That's how much excess speed it had. It's an object from around another star that flew past the sun. A dirty snowball behaved as dirty snowballs do. We will find more of these in the decades to come, so they're worth a passing mention. But the thing with comets is they're transient, temporary, ephemeral. This beautiful photograph by the Hubble Space Telescope is a photograph of Comet Schwarzmann-Wachmann 3, which in 1995 fell apart. We're currently tracking, I believe, 73 distinct pieces of this comet. So from one comet, now we have 73 baby comets. Comets disintegrate, they fall apart, they're ejected from the solar system, they crash into things, they're short-lived. And in the 1950s, a couple of scientists realized that this is a great problem. There were Jan Oort and Ernst Öpik, and they were looking at the long period comets. And they realized that these things are short-lived. Jupiter throws them away, never to return, they fall apart. Where do they come from? Well, the first default assumption you make as a scientist is maybe that they are the final representatives of a population that was once bigger in the past. Now, currently, let's say we get 10 per year, just as a number, long period comets. We get more than that, but let's assume it's 10. Half of those should be lost from the solar system within 1,000,000 years. You whittle away half of them in 1,000,000 years, which means if these are the last representatives of a bigger population in the past, 1,000,000 years ago, you'd have had 20 per year. 1,000,000 years before that, 40 per year, 80 per year, 160 per year, 320. That's only 5,000,000 years back, and we've increased by a factor of 32. Keep doubling 4,500 times, and you get so many comets that the solar system is solid ice, collapses into a black hole, and we are not here. We can't exist. So that idea just doesn't work. So what both Oort and Öpik came up with was that instead, perhaps there's a reservoir out there in the depths of the solar system that has an unbelievably large amount of cometary nuclei held in cold storage. And most of them are never destined to come into the inner solar system. But there's a trickle, a dribble of objects being nudged from that reservoir to replenish the population here. Just the same as Lake Wivenhoe is full of water, but there's a trickle of water flowing from it that eventually meets it to the ocean. If you're stood by that river and you look there today and tomorrow and next week, the level of the river will be the same, but the water molecules will be different. The water you see today will wash out to sea and be replaced by water from upstream. That's your long period comets. The reservoir from which the trickle is, if you go there today, tomorrow, next week, the water will be about the same level, but the water will still be there in the main. It's just trapped there, hanging around. So they hypothesized the Oort cloud, or the Öpik Oort cloud, this enormous sphere of cometary nuclei centered on the sun, stretching out halfway to the nearest star. For objects in this cloud, the sun may not even be the brightest star in the sky. For this to work, the Oort cloud must contain more than 10 trillion comets. That's 10,000 billion, 10 million million. It's a stupidly big number. And they hang around here, leftovers from planet formation, held in cold storage, but they get nudged and tweaked by everything. Passing stars give them a nudge. The gravity of the galaxy tweaks and moves things around, causing a steady trickle of them to fall in to be the next generation of the long period comets to keep the numbers topped up. For the short period comets, the story's a little bit different. They are again transient, but they have a different reservoir as their source. If you journey out in our solar system, nowhere near as far, you go beyond the orbit of Neptune, which is here, Neptune, Uranus, Saturn, Jupiter. You have all these objects, white, pink, and red dots. They are the trans-Neptunian objects, icy bodies held in cold storage left over from solar system formation again. And some of them eventually cross the orbit of Neptune and get scattered to become centaurs, the purple and brown objects here that I love because they're what I studied for my PhD. They bounce around, planetary pinball slings them in and slings them out. But about a third of them go on to become the next generation of short period comets. So we have a constant flux of new objects coming in to give us the beautiful comets that we see. But to understand how they got there, we've got to have an astronomical fairy tale. We've got to talk about how the solar system formed. Now, astronomy is weird as a science. If you do physics or chemistry or biology, you can do experiments. You can put things in a test tube and see how they react to acid. You can build a cannon and fire it. But with astronomy, all we can do is look. Everything we study is so distant that all we can do is observe it. And so what we do is we play Sherlock Holmes, we play detective, we gaze out at the night sky, we gather information, and we piece that information together in a narrative that is our best understanding of how things work. And we use that to make predictions, test it, refine the theory, back and forth it goes. And our theory of planet formation starts with dark clouds like the Coalsack Nebula here, the head of the Emu in the sky. Huge dark clouds of mass, of gas and dust floating around our galaxy that get nudged by passing stars and eventually begin to collapse under their own gravity. A few million years later, you have something like this, the Orion Nebula. So in that massive cloud of gas and dust, when things are pitch black, everything's collapsing in. Clumps within that gas and dust collapse to form individual stars. And you take material from an area so big, that enormous area of gas and dust collapses in, and a given star will form from material spanning a couple of light years of distance. An area so big light would take 2 years to cross it. But it's too dense, light can't get through. And that collapses down to an area just 1 million kilometers across, let's say. When you take gas and you compress it and you squish it into a smaller area, you increase the temperature, you increase the pressure. And that's what happens when you pump up a bicycle tire and the bike pump gets hot. So at the middle of these clumps of gas and dust, the temperature reaches 1 million degrees. Then it reaches 10 million degrees. That's when nuclear fusion can begin. A star begins to shine, and the radiation and the stellar wind it gives off will gradually blow away the remaining gas and dust around it, clearing a bubble around itself. What you're seeing here with the Orion Nebula is a cluster of baby stars called the trapezium, less than 1 million years old. Their radiation and their winds have blown and bubble a cavity inside that cloud of gas and dust until it's broken through the outside. So you're looking in 3 dimensions into the nest where the stars were born there. That's why you've got this beautiful clamshell structure. Now, the story of comets is tied to that. Around those baby stars that form, you get disks of material, which are the places where planets are born. They're disks full of dust and gas. The closer you are to the star, the hotter those disks are. The further out, the colder they are. So we look at a more complex picture. This is that same dust, but the stuff in the interior is hot and you get colder and colder as you go further out. So that means for any given species like water or like carbon dioxide, when you're too close to the star, you'll be too hot and it'll be a gas. When you're far enough away, it'll be cold enough for you to be ice. So you get the frost line or the ice line, a distance beyond which water is solid rather than a gas. Now, water is about the most common thing out there, as I said earlier on, which means that beyond the ice line, you've got lots of solid material. Planets grow much quicker, they grow much bigger, and that's how you get Jupiter and Saturn. But in that area, you form a huge amount of objects that are meters, tens of meters, hundreds of meters, kilometers across. They collide with each other and make bigger things than you grow planets. But a huge amount of those objects don't get devoured by one of the planets. They get scattered, they get flung away. A lot of them are scattered from the solar system entirely, never to return. But a large number, as the gas clears, as the dust is blown away, remain trapped in these reservoirs. The trans-Neptunian objects swept there by Neptune's outward migration, icy bodies that never got to form planets. The biggest of them, like Pluto and Eris, 1,000 kilometers and more across, the smallest mere meters across. Further out, you get the Oort cloud, objects that were flung away from the solar system, but not quite hard enough to escape, that passing stars then nudged and tweaked so they didn't fall back in. So you shroud the solar system with debris left behind from planet formation. That's our best understanding. And the thing is now, we can see this happening. This is so amazing. This is an image of the Orion Nebula in the background. But each of these are propylids, protoplanetary disks, imaged with the Hubble Space Telescope, where disks of material are forming planets through that very process as we speak. Now, that isn't the end of the story for comets. Comets' children are something I get very excited about, meteors, shooting stars. You see here a beautiful meteor shower radiating out with a time-lapse image stacking together images taken over quite a lengthy period of time there. And the story of these is tied to those beautiful tales. Comet McNaught again, shedding all that dust to space. As a comet goes around the sun, it gets close to the sun. It sheds gas, but it also sheds dust. The smallest particles of dust are blown away, never to return. But the bigger bits are shed from the comet, but follow it in its orbit. Some of them move a little bit quicker than the comet, some move a bit slower. And so initially, and again, I'm wonderfully good with paint, credit my artistic skills, but you've got a comet going around the sun, and every time it goes around the sun, it sheds some dust, and the dust initially hangs around near the comet. Some of it's spreading out ahead, some of it spreads out behind. And over time, the dust spreads out until it shrouds the entirety of that comet's orbit. That's all well and good. Now, these orbits are oriented randomly through space, but some of them cross the Earth's orbit and impedal our planet. Comets could hit us. And if a comet's orbit comes near the Earth, then every year as we go around the sun, we'll run through that dust and debris that it has left behind, and we'll get a meteor shower. So that's what gives us the wonderful meteor showers we see every year. A lot of them are old streams, so every year you get activity. But some meteor showers are fairly young. There's a bit of dust all the way around, but most of it's near the comet. So a shower like the Leonids, which occurs every November, most years is fairly dull. You'll get a few shooting stars per hour. But every 33 years, for a year or two, on either side, there's a chance of storms where instead of a few meteors per hour, you can get a few 100,000 per hour. That's when we're going through the swarm, the clump in the middle. And over the last couple of decades, we've learned a huge amount about meteor showers in the fine detail and the structure, which could easily be another talk or 3 talks. It's fabulous science. But all of this is thanks to those beautiful comets that we get to see. Now, it's well worth mentioning how these meteor showers work. You have all that dust shed behind moving in the same direction as the comet, the Earth moving through it. So we go through this material as it moves along, and all of the grains of dust are therefore moving pretty much parallel to one another as they move through space. But they hit the Earth's atmosphere. They all appear to radiate out from a single point in the night sky. We call that the radiant. And you see here, for the Geminids, meteors radiating out from the constellation of Gemini. Meteor showers are named after the constellation in which you find the radiant. What's happening here? Well, each of these flashes of light is a grain of dust ablating, essentially burning up 80 kilometers above our heads. It's not burning in the sense of a fire, but it's baking off due to immense heat as it crashes into the atmosphere. These are all moving parallel to each other, but coming closer to us. So what you're seeing is perspective. Every line on here, the tram lines, the pavements, the lines of the windows and the roofs, they're all parallel to one another. But as they're converging to the distance, they all converge to a point. We're seeing this in reverse. These meteors that we're seeing, all the dust is moving in the same direction, but coming towards us, they appear to diverge. That's why we get this experience of the meteors radiating out from a single point in the sky. Now, it's worth me mentioning in passing here, the annual highlight for us that we get every year, courtesy of something that has been described as a rock comet, an asteroid called Phaethon, that is on the borderline between being described as an asteroid and a comet. Every December, we pass by Phaethon's orbit and we get the best meteor shower of the year. We pass through dust that has been lain down by that object over thousands of years. For a couple of weeks, you see a few shooting stars, but on the nights of the 13th and the 14th of December, the shower peaks. If you're in the northern hemisphere, you can see up to 100, maybe even 150 meteors per hour on those nights, as the radiant point is high in the sky. We're further south, so the radiant is lower, so we don't get quite as good a show. But we're still in quite a fortunate place here in southeast Queensland, because that radiant still gets to a reasonable height in the sky. For us here in Toowoomba, the show will begin at about 9:30 p.m. in the evening. Before that, the radiant's below the horizon, which means the meteors are hitting the other side of the planet. When it rises, you're only going to get a few meteors in that first hour, but they're coming into the atmosphere at a really shallow angle, so they can go from horizon to horizon. As the radiant gets higher in the sky, the rates get better. Between about midnight and 4 a.m. is the best viewing, and then you could be able to see up to 50 per hour, if not more. This year, the moon is new, it's perfect. So if you're looking at camping, that's a good couple of days to go camping, particularly this year because the moon is out of the way. So 13th and 14th of December, I believe it's school holidays by then for those who are at the younger end of the audience. Persuade your parents to go camping. Have a lie in the morning before, and then lay up as late as you can. Wrap up warm, even though it's summer, or take warm things with you. Lay back, relax, tell each other stories, and experience what Uncle Wayne was talking about earlier on. That shared community, the beauty of sharing stories under that shared heritage of the night sky, and watch nature's fireworks blaze overhead. Now, the final thing I want to talk about tonight is a case of essentially the astronomical equivalent of buying a lottery ticket. Something I'm very excited about, but I'm talking about in cautious terms. At the start of January this year, a new comet was discovered. It was discovered unusually far from the sun, which for those who remember me talking about Kohoutek is probably ringing alarm bells. It was discovered when it was still beyond the orbit of Jupiter. Heading inwards, it was discovered independently by a large wide-scale survey called ATLAS and by a Chinese observatory that's often referred to as Purple Mountain Observatory. So this has been given the name of Shushan Atlas, and I'm probably butchering the Chinese name, for which I'm greatly apologetic. This comet will, at this time next year, be passing essentially between the Earth and the Sun, getting quite close to the Sun. It is very, very exciting. At the moment, this is where it is in the solar system. These figures are taken from Van Buitenen's website. This is a fabulous resource. You can twist and rotate this around, see the orbit in 3D and move things along. So the comet's here, it's still almost as far away as Jupiter is. Plunging in to duck down below the south pole of the sun and duck back up through the plane of the Earth's orbit in October next year. On October the 9th next year, this will be the orientation. The comet will be almost exactly between the sun and the Earth, between the orbits of Venus and Mercury. It's getting very close to the sun, which means it will get very active. Fingers crossed. It is also relatively close to the Earth, so it could get very bright. Forecasts of cometary brightness are challenging to make, especially for a comet that we've never seen come through before. And as we saw with Comet Kohoutek, comets can disappoint as well as surprise. Some comets are far brighter than expected, some are far fainter. So I'm laying on the caveats, but this is why astronomers are excited. And a lot of people in the room are going, you're excited, it's a graph, hooray. This is the forecast light curve for the comet. This is a prediction of how bright it will get. These numbers on the side probably mean very little to a lot of you, but this number here, 6.5, anything up from there is visible to the naked eye if you know where to look and is a fuzzy blob. The red line is a best fit forecast for how bright the comet is. These black dots are observations people have made. So draw that line across and you can see that for about 3 months, it might be visible with the naked eye as a faint thing. Magnitude 1 is the point at which you only have 50 stars in the night sky brighter than that. Magnitude 1, it could well get brighter than that. The forecasts are that it could even get up to negative magnitudes. It could be as bright as the brightest stars in the sky. On top of that, because it is passing through so perfectly between us and the sun, there is a temporary window where it might do something really astonishing. There's this thing called forward scattering that you get with dust, where basically dust is very effective at deflecting light very slightly. So we've seen with many comets in the past, if they are particularly dusty, if they're giving out a lot of dust, and they do what this comet is going to and pass almost perfectly between us and the sun, for a few degree window on either side of the sun, the brightness of the comet can increase by up to a factor of 100. This is really effective. We do not know yet whether this comet will be dusty or gassy. We don't know whether this will happen. But that little green bit there shows you what would happen if forward scattering were to come into play. And at its brightest, that would be as bright as the planet Venus, visible with the naked eye in daylight, if you know where to look. This has the potential to be the next great comet. I'm really excited about it. We'll get a better feel for it March, April time next year, as it's on the climbing side of the slope. But the caveat with all that is this fabulous quote from cometary scientist David Levy. Comets are like cats. They have tails and they do precisely what they want. Comets are hard to predict. Comets fall apart, they disintegrate. Sometimes when they fall apart, they fade to nothing. Other times, like Comet West, when they fragment, they get a lot brighter. The image in the background here is Comet Kohoutek from 1973, which shares a lot of similarities with the comet I was just talking about. Discovered unusually far from the sun, people got really excited about it. Kohoutek disappointed, but it was still as bright as the brightest stars at its best. And in all honesty, if this comet is as much of a disappointment as Comet Kohoutek, I will be absolutely delighted, because next year when we do the festival, we'll be able to show you it in the western sky in the evening when we do the stargaze. But just remember, comets are like cats, and while that's our best bet at what they'll do, they do whatever they want. So with that, I will bring the lights up, and thank you ever so much for your attention, and take any questions you have for me. Thank you so much.
Thanks for the lecture, really liked it.
Thank you.
I have a question regarding the formation of the solar system. So you showed the visualization where the gas is coalesced, sort of like a planner. It's a disk kind of a collation.
It's a thin disk.
Why does that happen? And a bit related to those planets all revolve around the disk. Does this comets also follow the same trajectory of rotations?
Fabulous, fabulous questions. And there's a couple of parts to that. So the first one is why you get a disk. So the material collapsing down to form the star is from a huge cloud that is not perfectly stationary in space, because nothing is. You get nudges and tweaks. So it has a tiny bit of rotation. These huge clouds will rotate with periods of millions of years. But if you've, and I'm terrible at this, so my apologies for fall over. If you've ever watched dancing or ice skating, and you see people do a pirouette, and then they bring their arms in, and it speeds their spin up, right? It's the conservation of angular momentum, and they're a lot better at it than I am. So the more you bring things in, the faster they spin. So from a cloud spinning with a period of millions of years, you get a star in the middle spinning with a period of a few days. That's the amount of spin up you get. Tied to that, you get this preference for things to fall into a disk. Now, the physics of it get quite complicated because you've got angular momentum, you've got a rotation axis, rotation plane where things are most commonly rotating in. Things coming in above that plane and below it will tend to get damped down to flatten out to that plane. But the best analogy I can give you, the physics is slightly different, but there's an analogy that we see in day-to-day life that does the same thing with rotation and disks. It's if you see someone making a pizza base, they get a really elastic dough, and if they're show-offs, they fling it in the air and spin it really quickly and keep catching it, and it flattens out into a big pancake. Same kind of thing. Different physics, I will admit that, but it's a similar kind of process. So you've got this material falling in, and the conservation of angular momentum makes it spin quicker, and that has a tendency to also make things collapse down into a disk as well. That then is why the orbits of the planets are pretty much in the same plane, because they're formed in that disk. The orbits of the comets are more spread out from that. Now, the short period comets, in the main with a few exceptions, have tilts from that plane of up to 30 or 40 degrees. They're mainly near that plane, because that matches the distribution of things in the trans-Neptunian objects. It's a puffed up disk, but it's definitely a disk rather than a circle. You do get some that are at higher tilts, but that's because when they encounter the planets can fling them all over. So you can increase the tilts, decrease them. The long period comets will move on all orbits of all tilts. Many of them go around backwards. And the reason for that is that when they're out far enough from the sun, nudges from passing stars make them spread out into a circle around the sun, a sphere, rather than a disk. So initially, they're all being ejected roughly in a disk. But when they're far enough away, everything stirs them up. And so over billions of years, they've smeared out so they're in a sphere around the sun, very tentatively held to us, and they're constantly being nudged and their direction changed. They're that far from the sun, they're traveling really slowly, kilometer per second or less. So a change of speed of 100 meters per second can change your direction quite drastically. So they get stirred into all directions so that when they fall in, they can come from any direction. So the long period comets tend to come in from all directions. We often describe them as isotropic comets, which means evenly distributed across the sky. The short period comets tend, in the main, to be concentrated nearer to the plane of the solar system because their parent population is nearer the plane of the solar system. And that's because it's so close in that the gravity from the sun really dominates and the distant stars can't stir it up. You need to be at least 1,000 times further from the sun than the Earth is before the galaxy passing stars can start stirring your orbits up significantly. The trans-Neptunian objects are only 40 or 50 times further from the sun than the Earth is, so they're very much dominated by the sun's gravity. So hopefully that answers all of the bits of that fabulous question. Thank you. We've got a question just over here.
Just with Comet ignored, sorry. I asked Nicholas when he was a baby if he remembered seeing it, but he didn't. But my wife and I would have an early dinner with the kids and we'd go out to Well Camp where the airport is. And, well, before it was there. And we would watch the comet set, and then we did that for about 10 days, I think. And then, but driving back in the combi van, just looking in the rear vision mirror, I could see the comet in the rear vision mirror.
Yeah.
It was amazing time. And one other question with the comets, the theory that the oceans were formed from comets, has that been confirmed yet, or is it still a theory?
That's very heavily debated. And I think there's a film reviewer in the UK who's fond of saying other opinions are available, they're wrong, but they're available. This is one of those topics that gets people very much the same way. The issue here, for those in the room who aren't familiar with this story, is that where the Earth formed, we're close enough to the sun that we are well within the ice line, we're within it, so it's hot. So water should have been a gas. And the Earth's gravity as it was forming is not strong enough to grab hold of gases. We couldn't just suck up an atmosphere. So where did the water come from? Now, the Earth is an incredibly dry planet. And I say that being aware that it's the wettest of the terrestrial planets. But when you think about how common water is in the universe, it is like the most common thing. It's so abundant because it's the first and the third most common atoms bonded together. So a wet planet, you'd expect to have thousands of kilometers depth worth of ocean, and we've got a little bit. Now, that makes sense. We formed somewhere where it was hot. Now, there are different theories about where the water comes from. Some of it is what people describe as endogenous or local water. The idea is that the silicate material that makes up the Earth, the molecules, the objects that were forming could trap water molecules chemically and also within the lattice of the objects, because you're forming from fluffy grains of dust, you can actually trap things. This is a process called clathrates, I believe. I'm not a chemist, but you have the chemical structure forming a cage around a molecule and trapping it. You also get hydrated silicate compounds. So there is an argument that some of the Earth's water was formed that way and was erupted through volcanoes from the mantle. Then there's the argument of exogenous water, which is water delivered from beyond. And there's two flavors of that. One is early delivery and one is late delivery. So we called early exogenous and late exogenous. But the idea is that the water was delivered from beyond the ice line, possibly from the outer parts of the asteroid belt, which are beyond the ice line, and possibly from comets. The truth, despite the fact that people will argue black and white, they'll argue it is either A or B or C, is that all of them will have contributed. The thing that to me is telling that suggests that the water is primarily exogenous is that the fraction of water on the Earth and Mars and Venus is a bit different. Now, I did some work back in 2007, 2008. Most of my work is actually computational. I run a clockwork universe and see where things go. And one of the things that really bugged me is that people always assume that the Earth, Venus, and Mars got the same amount of water from the same sources, which doesn't make sense to me. You've got multiple sources in different locations. So I ran some simulations looking at impacts on the Earth and Venus and Mars from comets and from asteroids. And what I found, it's really clear-cut and it's really obvious when you think about it, is if you set it so that the Earth gets one asteroid per comet as a ratio, and it won't, the Earth will get more of one than the other. Mars will get more asteroids per comet than the Earth does, and Venus will get more comets per asteroid than the Earth does. Because for something flung in from Jupiter, the difference between Mars's orbit and Venus's orbit is fairly small. Something coming in from the inner edge of the asteroid belt, Mars is right there, but there's a long way to go to Venus. So you get this effect where the contribution from the different reservoirs will actually be different between the planets. added to the fact that impacts through collisions are random because you either hit or you don't, added to the fact, and this is why it gets complex, that the Earth and Mars, and possibly Venus as well, experience giant impacts that stripped away their mantles and crusts at times, which would have removed a large amount of the water. So what the end result is that you get planets that have this chaotic history where each one has its own unique story. And the final stage of this, which I think is future work, you have those three different sources, and you can break it down as local, asteroid belt, cometary material, even more distant cometary material. There is potentially a way to test for them. So a colleague of mine in France, Olivier Moussi, is an astrochemist. And one of the things he's done a lot of work on is fractionation of isotopes. So you don't just have hydrogen, you've also got heavy hydrogen, deuterium. And what he's modeled and is shown is that from the ice line outwards, the amount of deuterium in water as a percentage changes as a function of distance because the temperature influences the chemistry. So you might actually have a signpost that tells you where an icy object formed by how much deuterium it contains in its water ice. If we can then relate that to the water ice, to the water on the planets, we can possibly start to infer where it's from. But the problem then is you've then got 4.5 billion years of chemical processing of the water that's happened afterwards to disentangle. Now, that's a very convoluted answer. The too long didn't read is we don't know yet. But this is the beauty of science. Those questions of why we still do science. We're at the beginning of the journey, not the end. Because we're still learning these things. And we are like kids exploring in the dark. We're still making our first discoveries. So I think if you ask me that again in 10 years' time, it'll still be an I don't know, but it'll be more certain I don't know. But we'll get there in the end. No problem.
But we do have a question online.
Okay.
Paul has asked, do you think he is asking, do you think life could have come from comets?
Yeah, so the question is, do you think life could have come on comets? And this is a question that would have been, this fabulous question that would have been laughed out about 30, 40 years ago, because the ideas of life beyond the Earth come in and out of fashion. And at the minute, we're in a period where we talk a lot about life beyond the Earth. There is a theory called panspermia, which is the idea that you can transfer life between planets and even between planetary systems. And for a long time, that was viewed as laughable science fiction. I know a lot of people who have been very scabrous of that as an idea through the years. But the bizarre thing is, the more experiments we do, the more it seems it could actually work. So people have done experiments in impact science, looking at the kind of big impacts like the dinosaur killing impact. And what they've found is that you dig a big crater and you can eject rocks into space. But there is a certain range of distances from the crater where the shockwave is strong enough to eject you from the planet entirely, never to return, but weak enough that it would not sterilize that rock or shatter it. So you've got this size domain where you can eject rocks intact from a planet. You then have the question of, well, that's all well and good. You can eject bacteria, but they'll die in space. And there have been experiments done where people have taken bacteria into the vacuum of space, left them for months, brought them back to Earth, and you're able to still culture them. Now, the amount of viable bacteria drops over time because you're exposed to all sorts of nastiness in space. But you only need one bacteria to survive. And when your rock lands somewhere else, it can inoculate it. Now, the quickest you could get a rock from the Earth to Mars is about 6 months. We've done experiments that show bacteria can last that long. And because that's the quickest you can get from the Earth to Mars, with 4.5 billion years of impacts, life has almost certainly been transferred back and forth between the planets. Whether it survived on entry, we don't know. And that's why I think if we find life on Mars, it'll be really interesting to see if it has a shared heritage to us or not. If it has a shared heritage, if it's got the same background as us, the same origin, it tells us that panspermia works and life can be transferred. It's a short step from that then to being the rocks that are ejected carrying life can become embedded in comets because they'll collide with them as well. Comets are fluffy enough that that impact would embed it quite deep, so it would then be shielded. Comets are ejected from the solar system. We saw comets from other systems coming into ours with Borisov. So comets could seed life in the cosmos if panspermia works. It was viewed as a laughingstock as a theory for very long, but every test that anybody does suggests that it can actually work, which is mind-boggling. And so it is possible that comets and asteroids help to transfer life around in the solar system. It's possible that if we find life on Mars, it could share a heritage with us. We could even be Martians. We could have originated on Mars. And it's certainly possible that comets could transfer life around the cosmos. But there is a long leap from saying that it is possible to saying that it did happen. And we're not at that stage yet. Part of the reason this theory is laughed at in the past is that there have been some very hyperbolic claims that were very easily disproved. One of them is quite a famous scientist who had lots of really good ideas, but also lots of crazy ones, Chandra Wickramasinghe, who worked a lot with Fred Hoyle in his younger days, had this theory and a bunch of evidence that the Perseid meteor shower that happens every August, through the 80s and 90s, was the best meteor shower of the year. The Geminis have now supplanted it. That happens every year, a couple of months before the flu season starts in the Northern Hemisphere. And so one of the things that he'd proposed was that the new versions of flu that are coming out that nobody had ever seen before were being delivered by the meteors in that shower, and that the smallest particles which can come through intact, the Brownlee particles, would take a couple of months to diffuse down, which would work. He even linked it to a series of events called red rainfalls that happened in India. That idea is widely considered to be hogwash. It's really not viewed very favorably in the scientific community. But it's something we've got to be careful of when we're discussing controversial ideas, which is that the way that we move forward is by having remarkable ideas and putting them to the test. The problem comes when you put forward ideas that have already been disproven, or you use your platform to put forward ideas that are palpably stupid to generate your own profile. And neither of those was true of the work Wickramasinghe did. He was controversial, but he was genuinely trying to do good science. I bring that up, though, to caution people about the stories of the Harvard astronomer that keep making it into the press. The alien spaceship that crashed south of Papua New Guinea, the alien spaceship that we observed a few years ago in the form of Mau. That is where it becomes scandalous for me. And it's this person, unfortunately, keeps digging up old theories that are long since shot down without reading the literature, claiming them as his own. Then when people say, no, look, really, people talked about this 50 years ago and it's clearly wrong and we've disproven it, he says, how dare you pick on me, you're so mean, and builds this martyr type thing, and has been incredibly successful in leveraging the media and building stories and illegally invading the waters around a sovereign country to float a submarine down and steal bits of stuff from the seabed to claim that they're alien spaceship fragments. So when you see stories about his work, please exercise due skepticism, I guess is what I'd say there. But not everybody who comes up with controversial theories is problematic like that. And in the case of Wickramasinghe, there were very interesting ideas that were worth raising and discussing, and they're testable. And they're testable and they've been shot down, and that's how science progresses. But that has given a bit of a reputation that means that the idea of life from space, panspermia, is still trying to shed that mantle of controversy, I guess. So hopefully that's it.
Yep. The comment we've had is a thanks from Robert, and enjoyed both talks very much. So thank you.
Thank you, Robert. Do we have any more questions from the room? Yes.
So when I was little, I studied that all the higher elements, they form in the sun. Now I'm just get puzzled of where does this water form? Like, we need oxygen, but then if it started in the sun, then how it ended up outside to form water and then form ice?
It's a wonderful question, and you are right. Everything heavier than hydrogen and helium and a tiny bit of lithium were cooked in the furnaces of stars or formed in stellar collisions and supernovae, a lot of complex processes. The oxygen that we have is not oxygen that formed in the sun. It's oxygen that formed in a previous generation of stars that lived and died and spread their remains into the cosmos. So every generation of stars is formed essentially from the corpses of the stars that came before. And so the cosmos is getting more and more polluted in heavy elements. So you're entirely right. Everything that makes us other than hydrogen, was grown in the furnaces of stars, but it's the furnaces of stars that have lived and died before the solar system formed. And that's where the phrase, we are stardust, comes from, essentially. So, fabulous question.
So you said about the comet that was between being an asteroid and a comet?
Yes.
So if they do break up, how do they get the ones that you can find on the surface of Earth?
Really good question. There's a few parts to that. So the thing about the thing that was partway between an asteroid and a comet is because in actuality, there's a total continuum. Asteroids in the olden days were things that didn't give off gas and dust, and comets were the things that did. And it's linked to what they're made of. But if you have a comet and bake it for long enough, all the icy stuff is taken away and you're left with just the rubble, so it looks like an asteroid. Similarly, if you've got an asteroid that formed far enough from the sun, it can have water on it as well. And it's only when it comes into the inner solar system that it would then look like comets. So it's a blurry line. They do break up and burn up, but some of them make it to the Earth in the form of meteorites, which is what I think you were talking about in the second part. And that's to do with things hitting the Earth's atmosphere, making it through. Now, there's an entire size range of things that can hit the Earth, from things smaller than the grains of dust in this room to things bigger than cities. There's a lot more of the small ones. The very, very tiniest things we call Brownlee particles, and these are the dust grains that are smaller than the width of a human hair. And they come in, and they're small enough that the most distant parts of the Earth's atmosphere, more than 100 kilometers up, can slow them down before they get into the atmosphere thick enough to burn up. So they slow down and they just float down. And they come down to the Earth a bit like dandruff. So when you're walking around outside, you're getting space dandruff on your shoulders. You get bigger than that, and you get deeper into the atmosphere before you feel the atmosphere. The atmosphere is denser, and then you plow the atmosphere up in front of you, pile it up, and it gets really hot. And that heat bakes you away, ablakes you. It basically turns your solid to gas, and you burn up. That's when we get meteors, and they typically burn up about 80 kilometers up. As that bit of debris gets bigger and bigger and bigger, it will punch deeper and deeper into the atmosphere before it's totally burned away again. Now, if it's a single piece that has internal strength, you can see that the bigger it gets, the deeper it gets into the atmosphere. Eventually, you get deep enough that you've slowed down enough that you stop burning up and you fall freely to the ground. So there's a size range that is probably comparable to the size of my fist and bigger, that when they're strong enough, they can make it to the ground. So stony and metallic material can punch all the way through once it's big enough to survive until it's slowed down. And those kind of meteorites are the most common, and they fall at terminal velocity. So they'll land in your backyard essentially at the same speed that somebody who jumped out of an aircraft would land in your backyard if they forgot their parachute. And it will cause even less mess than somebody who fell into your backyard without a parachute. They would actually be cold to the touch rather than hot to the touch, because they slow down by the time they're 10 or 20 kilometers up and then fall at terminal velocity, so they spend several minutes falling. And they've been burning super hot, but only on the outside. And they're like deep fried ice cream, essentially. The outside is really hot, but they're very insulated. The interior is still as cold as the depth of space. So when they land, the cold winds and they're still really cold. So you might see water condensing on them rather than steaming. Eventually, you get big enough that it's unlikely that a single bit is one thing, but it's more likely to be a clump of rubble held together very loosely. Cases like that, where you could be talking meters or tens of meters across, eventually that thing will fragment and you'll get a runaway explosion in the air called an airburst, and very little of that will make it down to the ground. And that's what happened over Russia with the Chelyabinsk impact in 2013, with the big spectacular fireball, 1,500 people injured, big bad news. Then you keep getting bigger, and eventually you get so big that you just don't see the atmosphere. And that's where you're hundreds of meters or kilometers across. And that's rocks like the one that killed the dinosaur, that just crash into the Earth at huge speed, make big craters. And so you've essentially got three different size ranges that make it to the ground. Some of those will be bits of comets, but cometary material is very fragile. So of all the meteorites we've found or we've seen fall, only one, which is a Tagish Lake meteorite that we recovered, is thought possibly to be cometary material, because cometary material is mainly ice, and if you put ice on Earth, it melts. So it's hard for them to get through. So most, if not all, of the meteorites we've found so far are from asteroids, not comets. But that doesn't mean in the future we won't find them. So hopefully that clears up everything around that question. Brilliant, thank you.
So with the forgive me, I've forgotten the whole the terms, but when you were talking about the Earth going past the ring of comets and
the dust.
Yeah. Have we found any big enough to cause major damage to the Earth that we've been able to predict, that we've been able to?
It's a really interesting question. And this is one of those things where I could have taken different points in this talk and branched off and given 5 or 6 different talks. There is a huge amount of debris in the solar system, and with everything, you get more small bits and big bits. One of the biggest debris streams we go through in a year is called the Torrid Stream, and it's active now. It's been active for a month. It'll be active for another 2.5 months. But at its best, you only get 5 or 6 meters per hour. But because we're going through it for 3 months and then again for another month elsewhere in the year, we spend a third of the year going through this, and we get more material from it than every other meteor shower combined. We think that is the remains of a comet that was more than 100 kilometers across that fell apart in the inner solar system more than 20,000 years ago. And every planet in the inner solar system goes through this debris, right? So most years you get a few meteors from it. You do get quite a few bright fireballs, and a brighter meteor means you've got a bigger bit or something coming in quicker. All material from a given stream comes in at the same speed, so a brighter meteor in a given shower is a bigger bit coming in. We have seen that within the torrid stream, there's a denser filament, which every now and then runs into the Earth and runs into the Moon, and we see an increase in the number of bright meteors and very bright meteors. We have seen flashes on the Moon of impacts of that debris hitting the Moon. We've seen fresh craters being formed. And it's likely that in the torrid stream, there are objects up to 1 kilometre across. We found most of the really big bits. Back in 1908, over Siberia, over Tunguska, there was an explosion that was the biggest impact on Earth in the last 1,000 years. It was probably a 100-metre sized cometary fragment that did the airbursting we were just talking about, blew up in the atmosphere. That was probably part of that torrid stream. That did no damage because it was in the middle of nowhere, but had it hit Earth 2 hours later, it would have leveled the whole of St. Petersburg and millions would have died. And that will happen again. It's not a question of if, it's not when. Now, that is something that will happen, but most of the Earth is empty space. So there is a threat, but it's not particularly high. But there are things in these meteor streams that can pose a threat to us. It's just the bigger you are, the less often things that size will hit us. So hopefully that answers the question.
Yeah,
Yes.
hi, John. Look, John, I'm just wondering about the chemical composition of all the objects out in the Oort cloud.
Yes.
How much variation is there, or are they all the same?
They are going to be, it's a fabulous question. And the most complex answer is that the full diversity we don't know. But the reality is that material will have been ejected that formed all distances from the sun. Because the stuff forming in the inner solar system, some of it will be scattered out as far as Jupiter and then flung outwards. So there will be stuff in the Oort cloud that looks like the asteroid belt. There'll be stuff in the Oort cloud that looks like the long period comets, the icy objects. And there'll be a full spectrum of variability in that because these objects all form through collisions. There will be fewer big objects and small objects, but there is a statistically realistic chance that there could be comets in the Oort cloud as big as the Moon and potentially even as big as the Earth. Because there will have been objects that size formed in the area where Jupiter is forming. Some of them will have been ejected, some will have ended up in the Oort cloud. We don't know what the biggest object there is because the Oort cloud is so far away we can't actually see it. We just know it's there because of the children that it gives us. In the same way that I guess if you're in Brisbane, you can tell that there's been rain upstream even if you've not seen it when the river rises, same thing. So we can tell what's happening out there. The full diversity, though, we don't know. There is even a suggestion that some fraction of the material in the Oort cloud will have formed around other stars. So the objects in the Oort cloud are very tenuously held to the sun, and other stars have their own Oort clouds and they're brushing against each other. And if you get two stars passing by each other with the right orientation, some of the comets might be moving this way relative to their star as they go around it, as the sun moves past this way, so their relative speed to the sun is slower than their star speed to the sun is, and they could be captured by the sun. And some of our comets could be captured by that. Now, that's still controversial, but it means that a small fraction of the long period comets that we see over time may well have formed around other stars and have been swapped in and out of the Oort cloud. So it may even be that the composition is reflective of more than just our star. Yes, and the variations in chemistry are something that is fundamentally really important to people studying exoplanets, because that process that we were talking about the furnaces of stars enriching the universe in heavy elements is changing the compositions of the disks from which planets form, which means that everything that forms in them will have different balances of the heavy elements, different amounts of carbon, silicon, stuff like this, and that will reflect in the objects that they form. So one of the things that was interesting with Comet Borisov were the differences in its isotopes, in these isotopic abundances compared to solar system comets. It was relatively similar, but it was different enough that even with a brief window, people could pick hints of the difference up. So we'll learn more in years to come with that. Fantastic. I think we had a question just in front of you there.
The comet that you pointed out that was around and visible in 44 BC, did that have a name?
It became known, well, it's a great comet of 44 BC, but it's also known quite often as Caesar's comet because of the cultural history that goes around it. That was an oddity. It was a comet that was probably as intrinsically bright as Hale-Bopp, if not brighter. But there is some debate over whether that means it was as big a cometary nucleus as Hale-Bopp, or more likely it was a comet that fragmented. And when you fragment into a few pieces, you increase the surface area, so you increase the activity. And so comets can display quite spectacular peaks in brightness. Now, the brightest comets of the last few thousand years have almost all been what we call the sun-grazing comets, Kreutz sun-grazing family. And there's something, again, I could give a talk about. The Caesar comet wasn't one of those, but nearly every one of the brightest comets that have been seen in daylight have been. And they're fascinating. The thinking is that in 323 BC, an enormous comet came so close to the sun, it's almost skimming its surface, but it's moving on about a 600 to 700 year period. And in 300 BC, it broke into two pieces. When those two pieces returned, well, maybe multiple pieces, there are some reports from about 300 AD that report 7 naked eye comets in the sky at once, which could have been the return of that. And that family is then continuing to cascade, fragmenting at every apparition. So Comet Ikeya-Seki, which was probably the brightest comet in the 20th century back in 1967, was one of those sun-grazing fragments. The Great Comet of 1843, which is probably the brightest comet that we've seen in the last 200 years, was one. All fragments of this same collisional fragment, this fragmentation where they're getting so close to the sun, they're getting torn apart. And we've seen thousands of mini baby comets in that family, because there's lots of little fragments that are a few meters across coming in, and they don't make it past the sun intact. They fizzle entirely. So the observatories that look at the sun from space, SOHO, has found hundreds of these little mini baby comets that fall apart as part of these fragments. Thank you so much for joining us. I do really appreciate it.